My proposal tonight is about quinoxalin derivatives and free radicals. First we'll talk about what are quinoxalins. Quinoxalins are small organic molecules consisting of two fused rings. One of the rings has two nitrogens in place of two of the carbons. Over here is a picture of the simplest quinoxalin molecule, quinoxalin. This is the simplest synthesis of the quinoxalin molecule. It's formed by the fusion of 2-nitrobenzamine, also known as 2-nitroaniline, and 1,2-ethane-dione, also known as glyoxal. There are a lot of applications for quinoxalin molecules. Some of the applications in industry are in inhibition of metal corrosion, preparation of porphyrins, electroluminescent materials, and many others. Some of the biochemical applications, which is where my research is kind of focused towards, are there's quite a bit of them. There's antibacterial, viral, fungal, parasitic, specifically anti-tuberculosis is one of the big ones, diabetes, cancer, neurological disorders, replacement for NSAIDs for anti-inflammatory purposes, and prevention of atherosclerosis. This is the structure of the derivatives of quinoxalin that I'm going to be studying. They're called quinoxalin di-N-oxide derivatives because they have two oxygens attached to the nitrogens. These molecules are very important in a lot of ways. They have the ability to absorb and donate single and pairs of electrons, so they can act as an antioxidant. They can also generate free radicals in hypoxic environments such as tumors, which makes them very useful for anti-tumor medications. The conjugation of the molecules allows them to absorb light very intensely, absorb and emit light, and makes them useful for dyes. So why would we want to research the quinoxalin di-N-oxide derivatives? Well, we don't really understand how they absorb and donate electrons, and if we discover how they absorb and donate electrons, we can create more useful derivatives. Specifically, with this research, we can look at how these molecules can be used as treatments in tumors and neurodegenerative disorders and anti-inflammatory disorders by absorbing and donating electrons. The research we have completed so far has been electrochemical analysis using cyclic voltammetry. This was done before this phase of research. The current phase of research has been using computational analysis. We use the computational program WebMo with the programs GAMES and MOPAC. These are all computational chemistry programs that use quantum chemical equations to determine the structures and the characteristics of molecules using a lot of theories. We started by creating 60 different structures, 20 derivatives, each with no absorbed electrons, a radical form, and a form with 2 absorbed electrons. Each of these was then optimized. The geometry of each molecule was then optimized using GAMES and MOPAC. These programs allow us to create the lowest energy state geometry of the molecule, and then can use this information to calculate quantities such as the Gibbs free energy. This is the base structure of the 20 structures that we created. We had substitutions on carbons 6, 19, and 20. which is 19 is here and 20 is here. And these derivatives had substitutions from as simple as fluorine up to a nitrogen and two oxygens attached. So we looked at each structure, we optimized their geometry, and then we calculated the free energy of the molecules. The next phase of research, we'll use Gaussian, which is more powerful than the programs that we have been using. We'll find a free energy change in the absorption and the donation of a single electron and a pair of electrons. We can use this free energy to calculate the redox potential. The redox potential tells us a lot about the ability of the actual molecule to absorb and donate electrons in the body or in a lab. We can then compare this theoretical potential value to the electrochemical data obtained in the earlier research. Because all of this research is done in a dry condition using theoretical models on a computer, there is not really a whole lot of safety issues. The only safety issue would be possible electric shock if maybe you spilled the drink on the computer. Some potential future research, after analyzing the more powerful, using the more powerful Gaussian program, we can compare the energy levels to electrochemical data, and then we can analyze the structures using NMR to confirm that the structures that we're expecting are the actual structures. We can then analyze these radicals with electron paramagnetic resonance spectroscopy. This can tell us a lot of information about the individual molecules, the radical molecules, and their structure. The initial costs of this are already paid. We have the computer system and we have the computational programs. The future cost, if we decided to do the electron paramagnetic resonance spectrometry, we would need the EPR spectrometer. This is pretty expensive, so this part of the research may not occur, or it may be a long time before it does occur. These are all the references I used to make this presentation.